All right, today we're going to do section 6.2, and this is trig functions of acute angles. Acute just means less than 90 degrees, but greater than 0 degrees. So anything between 0 degrees and 90 degrees is an acute angle. So right off the bat, this means your angle is between 0 degrees and 90 degrees. And so we'll deal with 6 basic trig functions, evaluation of those trig functions, and then applications. And so one thing I always try to tell people with applications is I can't do an example of every type of problem. Part of mathematics is being able to take what you've learned and synthesize it all together. So you can't always lean on, oh, this problem's exactly like this one, because most problems, like those that come up in life, are more comparable to math problems, because what you're doing is you should take your previous experience and your prior knowledge and be able to synthesize something new out of all of that. So again, just to reiterate, here's the unit circle. And so if we're dealing with acute angles, really we're only going to deal with this part of the unit circle, just this first quadrant. So don't really need anything else outside of or over here, so that's going to make this a little bit easier. So basic trig function. So assume theta is one of the acute angles in a right triangle. And we're going to let the adjacent and opposite stand, and let adjacent and opposite stand for, respectively, the lengths of the sides of the adjacent and opposite angle of theta. So if you think about your triangle, in keyword it's a right triangle, so here's a right triangle, and here's theta. Our adjacent side is the one right next to the angle. Our opposite side is the side, across from theta. And the hypotenuse is going to be the side above theta. So notice the adjacent side is the one that, and if you go, okay, well, what if the triangle was like the same thing but turned upside down? Then the better way to say it is the adjacent side is the side that's between the angle theta and the right angle. So that might be the better way to word it. But then we have sine, cosine, and tangent of theta, and they're abbreviated as follows, and these are the ratios. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And most people remember these through, I don't know who came up with this, but they deserve a gold medal for mathematics, because this is one of the few things that I think sticks with most people throughout their lives, even though they may hate math, they may not care for it. SOHCAHTOA pretty much sticks out with people. There was one company that made a video game that had a math loving villain, and his battle cry at the beginning of every fight was SOHCAHTOA. So it's even made its way into like mainstream media. So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. Like I said, this is probably the thing that if you're thinking trig, this may have been the first thing that came to mind if this was not your first experience with trig functions. Now, cosecant, secant, and cotangent. These are the other relations. The thing is, though, to me at least, it's just easier to not try and memorize, okay, cosecant is hypotenuse over the opposite side. Secant's hypotenuse over adjacent. Cotangent is adjacent over opposite. Just correlate these. Cosecant goes with sine, secant goes with cosine, and the only matching ones that get to go together are tangent and cotangent. So the first two cos don't go together, but tangent's friends with cotangent. That's the way it works in my head. I don't know why I say friends, but I also think of sine and cosine as having opposite personalities because something in calculus. It's a really weird thing. But the main way to remember these, cosecant goes with sine, so it's 1 over sine. Secant is 1 over cosine, and cotangent is 1 over tangent. So if we use that information, we want to determine the value of the 6 trig functions. So that's actually pretty easy here. So like I said, we're just going to bring in the unit circle for, well, we'll bring it in for the second one. So here's the way I always write them out. So I say sine of theta equals, and then I go cosecant of theta equals, cosine of theta equals, secant of theta equals, and then tangent of theta equals, and cotangent of theta equals. Now the reason for that is, remember, sine pairs with cosecant, cosine pairs with secant, tangent pairs with cotangent. So if I learn what sine is, then I just have to flip over my fraction, and I've got cosecant. So that to me is why I choose to do this. Now the thing is though, so we have our angle theta, cool, but we don't have, well, we're missing the hypotenuse. This is a right triangle, so if we call this side, we'll just call it H. No reason to make life hard. Then H will be equal to, based on the Pythagorean theorem, H squared is going to equal 4 squared plus 3 squared. So then we have that H is equal to the square root of 16 plus 9, which is the square root of 25. So that means that H is equal to 5. Now you may go, okay, well, what if, is it plus or minus 5? Let me pull this back up again. Make any triangle here in the first quadrant. Make any triangle in the second or third quadrant. Now I should have connected it all the way out. But the hypotenuse is a length here. Your hypotenuse needs to come out positive because of its positioning. Because technically what you're doing here when you do the, well, not even because of its positioning, but sometimes the Pythagorean theorem is referred to as the Euclidean distance formula. And so it's measuring what's the distance from this point to this point. Now here's the thing. If you have a distance and it's negative, that means you went backwards. So we need to keep this positive. So that's the reason that you always say the hypotenuse is a positive value. In this case. Sorry, in any case, not in this case. Tangent, sine, cosine, tangent can all be positive or negative. But when you're dealing with the components, your hypotenuse will be positive. So let's start putting these together. So I'm just going to write it down here. SOHCAHTOA. All right, so sine should be our opposite over our hypotenuse. So our opposite in this case is 4. Because remember, it's the opposite is the side that's on the right angle. adjacent is between theta and the right angle. So the opposite is going to be 4 over 5. Cosine is adjacent over hypotenuse. So the adjacent is 3, and the hypotenuse is still 5. Let me keep them all the same way so it doesn't look weird. And then tangent is going to be the opposite, which is 4, over the adjacent, which is 3. And then, like I said, because I know that cosecant is 1 over sine, what that means is just flip over your fraction. So cosecant is 5/4, secant is 5/3, and cotangent is 3/4. So that's kind of the easy way to go about this. Find sine, cosine, and tangent, and then you just do it. Now, if these came out to be a decimal, you would just do 1 over the decimal. But because it's a fraction, if you do 1 over a fraction, it just swaps the numerator and the denominator, which makes life really easy. Now, if we look at this next one, part B, so I'll write over here, so sine theta, cosecant theta, cosine theta, secant theta, tangent theta, and cotangent theta. So notice this one, I didn't have 2 sides. I've only given 2 angles. So now I need to use the other part of a triangle that we know, specifically a right triangle. Well, really in any case the triangle would work, but because it's a right triangle, this makes our life easier. So remember, this is equal to pi over 2, or 90 degrees. The sum of all the angles in a triangle should be 180 degrees. Well, 180 degrees is also pi, so that means if we want to find out what theta is, then we need to have pi is equal to theta plus pi over 6 plus pi over 2, not minus yet. And so if you do this, you can do it in a calculator, you can do it by hand. I'm just going to use a calculator to speed up a little bit of this, because I would just subtract over pi over 6 and pi over 2. If I can type it into a calculator. So after that, you would get that theta is actually equal to pi over 3. So now that we know what theta is, instead of going back to trying to find a ratio or find something like that, let's go here to the unit circle. Because now, remember, this is your hypotenuse. This is your opposite side, because it's opposite of theta, which is what we're after. And this is your adjacent side, because it's between theta and the right angle. Now, if I look, theta equals pi over 3. Which triangle is that? Well, that happens to be this one. So there's our pi over 3. And so now we're actually in really good shape, because one other thing that I want to bring up is on the unit circle, all of your x, y coordinates, those are equal to cosine of theta, sine of theta. So cosine is associated with the x value, sine is associated with the y value. So from here, we have that sine is the square root of 3 over 2. And then we also have that cosine is 1/2. But now to go back to tangent for a second, tangent is equal to opposite over adjacent. In reality, it's actually equal to the opposite over the hypotenuse divided by the adjacent over the hypotenuse. But because the hypotenuse would cancel out, because it would be like having 1/4 over 1/4 over 3/4, we treat tangent as opposite over adjacent. But tangent is also sine of theta over cosine of theta, which also means that cotangent is cosine of theta over sine of theta. So that's another way to think about these. When you don't have the given sides, but you do have the angle, this is the way that you need to go with it. That sine of theta over cosine theta is tangent. So now that we've discussed that, now I can actually figure out what tangent of theta is. I'm going to actually do that over here or down here. So tangent of theta equals sine over cosine. So it's square root of 3 over 2 over 1/2, which is square root of 3 over 2 times. So remember, this is fraction divided by fraction. So some people, there's a common phrase that gets used, but I don't like to say it just because I've seen too many people mess up from it. So then this is square root of 3 over 2 times 2 over 1, which then the 2's would cancel, and you're left with tangent is just the square root of 3. Now, anytime you have something like this, most of the time you're going to want to swap out, or if there's a square root in the denominator, most places like you to go ahead and take care of that. So the thing is, when we do sine of theta, we got that it was square root of 3 over 2 from the unit circle. But when I flip it over, because because cosecant is going to be 1 over sine of theta, which means just swap the numerator and denominator. That leaves me 2 over the square root of 3. Now, most places don't like 2 over the square root of 3, so to do what's called rationalizing the denominator, and I'm going to space this one out a little bit, because this one's a little bit cramped. My cotangent's going to have to go down here for this one. Actually, I'm going to write it over to the side a little bit. What you do is you multiply the numerator and the denominator by the same value, which is the square root of 3. And the reason I picked the square root of 3 is because that's what's in the denominator here. And then if I do that, I get 2 times the square root of 3 over, now I'm not going to write square root of 3 times square root of 3, because if I do that, that becomes the square root of 9, which the square root of 9 is just positive 3. Now you could say, well, it's plus or minus. Look at where we are. Sine had to be positive, and so did cosine. So that means your opposite side here and your adjacent side here also had to be positive. If this was in the second quadrant, then we would have to actually pay attention to it, because notice all the x values here are negative, but all the y values are positive. So depending on the quadrant you're in, that kind of determines what these are. So If sine's positive, cosecant has to be positive. If cosine was negative, then secant would have to be negative. That's just the way it goes. And then if we flip 1 over 2, we get 2 over 1, which is just 2. And then cotangent would be 1 over the square root of 3, which would just become square root of 3 over 3. Now, the reason I didn't show the algebra for that is just imagine instead of a 2 here, you have a 1. And so that gets you all 6 trig functions for this. And I actually had enough room, probably. I could have written it over here. But so that's how you find the 6 trig functions of an acute triangle, either knowing 2 sides and the angle is theta, or knowing no sides and just knowing the other angle, because then you can find theta using that. So if we wanted to evaluate tangent and secant of pi over 4, we're going to use a very similar process. So remember, tangent is opposite over adjacent, but it's also equal to sine of theta over cosine of theta. And secant we're also going to use as that it's equal to 1 over cosine of theta. So if I want to find the tangent of pi over 4, I just need to go over to here. So here's the pi over 4. And I know then that needs to be equal to sine of pi over 4 divided by cosine of pi over 4. And this one's actually works out really nice because when you're on one of these 45-degree angles, notice the sine and cosine are the same value. Their signs just may be different. And so when we're here, we get that tangent is, square root of 2 over 2 over square root of 2 over 2. Now, without having to do any algebra or anything, if you had 5 divided by 5, you know 5 goes into itself one time. Anytime you have the same number over the same number, it's just 1. Doesn't matter how big, how small, fractions, rational, irrational, you're still going to get the same thing. A number divided by itself is always 1, except if that number is 0. Don't want to get anybody the wrong idea that it's okay to divide 0 by itself. That one's still off limits. And then if I do secant of pi over 4, then I get that secant is 1 over cosine. So this is 1 over cosine of pi over 4. Now, sometimes I do the brackets, or sometimes I do the parentheses, sometimes I don't. Typically, like if you have sine plus something or cosine plus something, it's better to do this just so you don't accidentally include it in. One thing we're going to do momentarily is what if you don't have one of these nice angles? And the thing is, say you had sine of 56 degrees plus 5. If you do it, you're in a calculator and you just leave it like this, sine of 50, because a calculator, as soon as you type sine, it's going to give you sin open parentheses, and then you just start typing. If you give it this, it's going to treat it like this most of the time. Some calculators may not, but a lot of times you have to be very specific and say, okay, this is sine of 56 degrees, then you add 5 to it. So I don't have consistency about it, but typically like something like this, sine of pi over 4 over cosine of pi over 4, I kind of like to do that just to make it easier. So then the other thing, so I get 1 over cosine of pi over 4. So pi over 4, I have square root of 2 over 2. So this is 1 divided by the square root of 2 divided by 2, which is equal to 1 times 2 over the square root of 2. Now already I can tell this is not going to work out because, well, not that it's not going to work out, but I'm going to need to handle the square root in the denominator. So like before, my goal is remove the square root. And to remove the square root, I just multiply by what's under it. So this gives me 2 square roots of 2 divided by 2, which those twos would reduce with each other. And so now I have that secant of pi over 4 is equal to the square root of 2. So that one's pretty easy. Again, don't let the arithmetic or the simple algebra be what messes you up. Just be careful, take it slow, and you'll be okay. Now, one quick thing before we use the calculator. All calculators have a button that says mode. Now you may have to search for it, but typically a mode button is going to tell it to, or I'm using a Casio FX300ES. This is the same one I have had since high school, and it's still working, and I don't think I've ever changed the batteries on this thing. But some of them have a mode button, some of them have a setup button, but you always want to make sure that whatever you're dealing with, degrees or radians, that you have it in that given mode. Because if you don't, if you do sine of 90 and it's in radians, you're going to get the wrong answer because it's going to treat it as 90 radians. That's always a good quick check, is if you plug in, like, to go back here for a second, notice I said these were related to, that this was x and this was y. So sine of pi over 2 or sine of 90 degrees should always get you 1. So if you were to plug in sine of 90 and it doesn't give you 1, then you know that it's not, that it's in radians and not degrees. Or if you plugged in sine of pi over 2 and it didn't give you 1, then you would know that you were in the wrong mode. So first one's pretty simple. Let me double check my calculator. So sine of 56.4 degrees. So I go in, I check to make sure that it's in degrees mode. And because I'm paranoid about it, I will double check it. And so then I do sine of 56.4, and I get that that's equal to approximately 0.83. I'm going to stop it there, 3. Now, all calculators that are scientific should have a sine, cosine, and tangent button. But you notice you don't have a cotangent button. Now remember I said if you go back to the 6 that cotangent is 1 over tangent. So we will use that to our advantage, and we'll say that cotangent of 5 pi over 11 is equal to tangent of 5 pi over 11. Or 1 over tangent of 5 pi over 11. Now again, the last one we did in degrees. So let's do this one in radians. So in my case, I have to hit shift and then I hit setup. And then degree, I have to press 3. In radians, I have to press 4. But for whatever calculator you're using, usually the manuals are available online if you don't have it, or you can look up a quick YouTube video or something. So when I plug this in, you can either do 1 over. So you can, some of them will have a little fraction button that's like this. Or you may have to do, which then you can actually plug it in like this, or you may have to do 1 and then divided by tangent of 5 pi over 11. Either way is going to work. It's just a matter of which one you can use and which one's going to be easier. So then tangent of 5 pi over 11. Now, technically, I should say, if it won't let you do a actual displayed fraction, then you're probably going to have to do it like this. 1 divided by tangent of 5 pi divided by, not divided by parentheses, divided by 11. And if you want to be extra sure, you can put it in like this, and that will ensure that you have everything accounted for. All right, and then that comes out to approximately 0.144 if I round it to 3 decimal places. But so that's how you handle some of these on a calculator. If first things first, and I should have done it for B, I should have put it immediately in radians mode just to double check. And then once you have it in the correct mode, degrees or radians, then you choose, okay, do I need to do anything special about it? Because like I said, if it's secant, cosecant, or cotangent, you're out of luck with those. You have to do 1 over to accommodate it. Or this is another option. This would have been a lot more inconvenient, but you should be able to do cosine of 5 pi over 11 divided by sine of 5 pi over 11, because cotangent is cosine over sine. So that should also be another way that if you don't want to do 1 over tangent, but whichever way floats your boat, they should come out the same answer. Now, if you want to be very, very precise about measurements with degrees, you go degree, minute, and then second. Now, you go, okay, wait, degree, okay, no, that's an angle measure, but then you go to minute and second, and you go, that should be time. In this case, because of the way they work, it's 1/60th of a degree. So you can think about it like that, a minute and then a second. And then a second is 1/60th of 1 minute. So it's a 60th of a 60th, which is 1/3600th of a degree. Which means you're getting into very, very precise measurements. These are things that, I mean, you're talking probably you have to have like a NASA level telescope to be able to make this fine of an adjustment. Now, I'm not an astronomer or a stargazing enthusiast, so there may be commercially available telescopes that can get precise, but I feel like you need to have some serious tech behind it to be able to do 1/3600th of a degree. So that's just my 2 cents about it. Now, this is one good example. Say you see somebody who is surveying. Now, a lot of times they do this for construction sites, things like that. And that's a case where you probably do want to have some very precise measurements. So before you cut down a dead tree, you very sensibly decide to determine its height, because you don't want to cut down the tree and go, I think it's about 40 feet tall, and your house is 45 feet away, and it turns out the tree was actually 50 feet tall. Probably would not be the best thing to find out. So back up from the tree, and you're assuming that you can that the tree is basically going up straight. If it has a bend, it's basically negligible. And then you use a theodolite, I'm assuming that's how it's pronounced, which is a surveyor's instrument that accurately measures angles. And you get the angle between the ground and the treetop is 61 degrees, 55 minutes, 39 seconds. Now with this information, we can determine how tall the tree is. So if we do that, now first of all, make sure you're in the correct measurement. So last one we did was radians, so go ahead and throw it back into degrees. So 61 degrees, 55 minutes, 39 seconds. Which if we expand that out is 61 plus 55 over 60 plus 39 over 3600. Which is roughly 61.9275 degrees. Now, you can be as accurate as you want. The thing is, figure out just how accurate you need to be. We are to 4 decimal places, so we should have a pretty good idea of what it's going to be. You could go very overkill and keep 7, 8, 9 decimal places, but I forget, like with pi, I think you only need 60 digits of pi to accurately measure, I think it's like the radius of the universe to a degree of accuracy that's down to like atoms. So some things like that, you need 60 places of pi. This is the tree in your backyard, and you just want to make sure you don't have to buy a new garage after you after you cut down the tree. Probably 4 or 5, be okay. 7 or 8, you're getting into overkill territory, where it's not going to make too much of a difference. But now we can use the figure, and the reason you go, okay, well, why did I pick tangent? Go back here. Remember, tangent of theta is the opposite over the adjacent. In our case, we have the opposite, or we want to know the opposite, but we have the adjacent. Which means if I multiply both sides by the adjacent, I get that the adjacent times the tangent will give me the opposite side. And so because I need this opposite side, I'm in good shape. I can use these pieces of information. Now, if you go, okay, well, why didn't you use like cosine? Because that's adjacent over hypotenuse. Because we know the adjacent, we don't know the hypotenuse. That would be a long way to get around to using sine to find it. And that might add error on top of it for finding this diagonal, which would be rounded. Which then you have to use rounded information to find something else. So error compiles the more you have to round. So this is going to be the easiest way to go about it. So tangent of 61.29 or 9275 equals the opposite over 40. So the opposite is 40 times tangent of that thing, which is approximately 75. Now, 75 feet, let me be exact. Now, this may be a case where I would choose maybe not to round it too much. Let me double check. 40 times tangent of 61.9275. Oh, never mind. Yeah, that would be better to round up. 74.99995882. So, yeah, basically 75 feet. And this is a case where you may want to not follow math conventions and go, oh, well, it was 74.4 feet. I can just round it down and say that's 74 feet. 40% of a foot might make enough of a difference that you don't want to ignore it. So just make sure you double check those, because it may miss all of your house, but because you rounded down, you may take off a little chip of the garage. So just be aware. Probably some situations it's safer to round up, because this is a real world scenario. And so it was a word problem. Give a word answer. The tree is approximately 75 feet tall. And so this is an example that's using the accuracy of degrees, minutes, and seconds to show that you have a pretty good idea. Now, if you had done just 40 times 61 degrees, or 40 times tangent of 61 degrees, yeah, that comes out to 72.16. 72.16, you're missing 3 feet there. So there's a good chance you could take out the garage, or take out part of the garage with your miscalculations if you do that. And we'll do one more example. So the manufacturer of a certain brand of 16-foot ladder recommends that when in use, the angle between the ground and the ladder should equal 75 degrees. So what distance should the foot of the ladder be from the base of the wall it is leaning against? So we want the angle to be 75 degrees. So that's pretty easy. We're leaning it up against the building, so we're assuming this is not like some abstract painting build or abstract piece of a building to where it's all jagged. We're assuming right angle. And so the ladder in this case is 16 feet. So this is actually, we know the hypotenuse in this case. So we need to know how far back does it need to be. So we need this, which that's the adjacent side, because that's the side that's between the right angle and our angle theta. So we have the adjacent, the hypotenuse, and the angle. So going back to trig functions, cosine of theta should equal the adjacent over the hypotenuse. So right now I've got cosine of 75 degrees equals the adjacent side over 40. Or sorry, over 16. I still got the last one in my head. So that's why we'll use cosine of 75 degrees. Then once we do that, multiply 16 on both sides. That's going to give you adjacent by itself, which is going to give you roughly 4.14 feet. Now, if you're going, okay, well, how do I take this into account? So 0.14 is 14%. So you can say I need to find 14% of 1 foot, which means also if you want to break it down, you can say what's 0.14 multiplied by 12, because you need 14% of the 1 foot, or of a foot, to kind of figure it out. So 14% of 12 is 1.68. So this equals 1.68, which we can go ahead and just say it's approximately 2 inches. Because you're probably not going to be able to measure quite exactly 1.68. You could be a little bit more precise and just say 1.7, but might as well round it up to something even in this case. And so with that, we've done acute angles. Next up is 6.3, and that will cover it for this course. So we're almost done, and I can't believe it.